Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. Today we will continue with lecture 8 on the absolute motion analysis. If you remember, we have covered this in topic 6 for particles. Now we will cover it for rigid body. So absolute motion analysis refers to the technique of deriving the velocity and acceleration equations based on the geometrical relationship of the bodies. You can refer to the earlier technique developed in lecture 6 on the absolute motion analysis of particles. This knowledge is very useful in determining the kinematics of planar machines, because in this section we are limited to planar machines. And one example is the internal combustion engines. In this figure, for example, is an IC engine, which you can see is a relatively complicated piece of machines. It's three-dimensional and it has a piston and a connecting rod and a crankshaft together with the camshaft at the top, which drive the valves for the inlet and exhaust. And these are driven by some timing belt, which give us the relationship between the speed of the crankshaft and the camshaft. This is a full engine, relatively complicated, but when you look at the side view or the planar view of the engines, you can see that this can be represented as a planar 2D machines with this crankshaft, the connecting rod, and the pin. The others are just structures that are used to support the control the inlet of the fuel and also the outlet of the exhaust. And what happened is that when we represent it in our analysis, we simplify it to rigid bodies, where R is the crankshaft, L is the connecting rod, and P is the piston, and P is constrained to move in a horizontal or straight direction as the piston move in the cylinder up and down. Here you'll see that the piston P is constrained to move in the linear direction or in the horizontal direction. This is the way we reorientate to allow us to do the analysis. So what we want to do in a absolute motion analysis is to find the relationship, if there is any, between the piston and the angle of the connecting rod. Here the angle of the connecting rod is defined by phi, and the displacement of the piston is defined as SP. So when the crankshaft rotates, this piston will move left and right, and from there we will determine the velocity by differentiation of the displacement and getting the acceleration by differentiating the velocity. So what is key is to find the relationship between the displacement of the piston with the angle of the crankshaft. So this is why we said that it is to determine the relationship between the geometry. So you can see that there is a geometrical relationship, and you can see there is a triangle here, which we can find that SP equals to, simply put, if you look at this triangle here, let me write it down. You can see that there is a triangle, one triangle here, and there's another triangle there. So you can find the component, the horizontal component. This is, let's say, component 1, and this is component 2. So if you want to find the component 1, we can look at that triangle and say, the component 1 is SP1, for example, like equals to R. Let me write it here. SP1 equals to R, which is the crankshaft radius cos phi. And then what about SP2? It is L cos beta. Is there a relationship between phi and beta? There is. We can determine that using a trigonometric relationship. But what we wanted to show here is that there is an SP equals to R cos phi plus L cos beta. So that is, so if we then find the velocity of the piston is the differentiation of SP, and you can differentiate the, so this will give you the velocity. Similarly, you can proceed with the acceleration of the piston by differentiating the velocity against time. So they give you the acceleration. So this is a way of thinking how we use mathematics or the geometrical relationship to determine the velocity and acceleration of the machines. So let's see one simple example before that. So the procedure for analysis is quite simple. We locate a point P. We locate a point P using position coordinate and the other points which give the vector that relates the input vectors and the output vector. We measure the angular position of the link to a fixed reference line and write down the vector equation and differentiate the position vector to obtain the velocity vector and differentiate the velocity equation to obtain the acceleration vector. This is what generally being done before, and let's look at one example. Okay, let's look at one example here. Is a 2-meter long bar here is confined to move in the horizontal. This is the horizontal slot and horizontal slot A, and vertical slots A and B. Okay, so this is vertical slot, horizontal slot. If the velocity of the slider block at A is 8 meters per second to the right, determine the angular velocity of the bar and the velocity of the block B at the instant theta equals to 60 degrees. So we are tasked to find the angular velocity omega and the velocity of the block B, so VB, at the instant where theta equals to 60 degrees. So we know that theta equals to 60 degrees. So let's look at this solution, that technique that we've put 5. Identify datum, draw the second is draw the positive displacement direction, identify the relevant geometry, write the equation and differentiate to get velocity and acceleration. Let's see whether we can apply these 5 techniques to the solution here. So the first one is to identify the datum. So it will be quite easy to identify the datum. So I'm going to say that this is the datum for A and this is the datum for B. So that's datum. So this is number 1. I already identified the datum. So done. That's done. So we want to draw the positive displacement direction. That's number 2. So to me, let's put positive x this way. So this will be xa, and or x can be this one. Oh, we can identify this as the datum x. Okay, and this is the distance y. So I think we should find the right datums from here. So let's put the datum here, number 1. This is our datum 1, and then that's number 2. We identify the positive displacement as this one. So that's number 2. Yeah. So if you use our right hand here, we can find the xy position. So we already show our xy system to be like this, and we measure it from there. So third is identify the relevant geometry. So I think this triangle is the geometry that we want to look at. So that's our number 3. Number 4 is we have to write the equation for the displacement. I can see the relationship between x and the length of the rod, so I can write the equation for the displacement. X equals to 2 cos 60 degrees, or 2 cos theta, and y equals to 2 sine theta. Can you see that? This is y, 2 sine theta. This is y, and the sine component of this, and x is the cos component of that. So then this is number 4. We've done it number 4, and after that we going to differentiate. So if we differentiate x, we will differentiate dx over dt, and we will get x dot, that will be d over dt 2 cos theta. And then we have the answer to that is 2 minus 2 sine theta. To cos theta, we differentiate, we get minus sign, and then theta dot. And then we know that x dot is equals to VA. So VA equals to x dot equals to minus 2 sine theta. I'm going to replace theta dot with omega. Yeah. Similarly, we can do with dy over dt. And that will give us y dot and d over dt 2 sine theta. When we differentiate sine theta, and that's equals to VB equals to y dot equals to 2 cos theta, theta dot, that is equal to 2 cos theta omega. So we have that relationship that we can block this equation, VB and VA. Okay, so that we now know that VA equals to minus 2 sine theta omega, and we know that VB equals to 2 cos theta omega. So we need to find what omega is. We know what VA is. VA equals to 8, so that VA equals to 8 is minus 2 sine, what is theta? Theta is 60 degrees. And from there, we can get omega equals to minus 4.619. Minus 4.619 radian per second. So omega is this way. So from there, we can find what is the question asks us. This is the first answer. That is the angular velocity of the bar. And from there, we want to find what VB is. VB equals to 2 cos 60 degrees. And omega is minus 4.619. Yeah. And we can get VB equals to minus 462. Equals to lebih kurang minus 462 meter per second is going downwards. Okay. So can you try solving the acceleration? Case, yeah, using the same approach, you can find the acceleration. So let's try the acceleration. So we know that VA equals to 2 minus 2 sine theta omega, or theta dot. So AA would be d VA over dt. So d over dt. So we can find or differentiate 2 sine theta, theta dot. Okay, so that you can do that in turn. So you can find that that's equals to so you can rewrite AA equals to d over dt minus 2 sine theta, then theta dot, plus or plus minus 2 sine theta d theta dot dt. And you can try to solve that in parts. Yeah. So not so difficult. We have done that before, so I think you could try that on your own. Let's do another examples here. So this is another example where, in this case, the end of the rod R, this is the rod R, maintains contact with the cam. This is a simple cam, a circular cam, by means of a spring. So you have a spring that pushes the rod, and the rod is in contact with the cam. If the cam rotates about an axis O, so there is a pivot point here, okay, with an angular acceleration, so it rotate with an angular acceleration omega and angular alpha and also angular velocity omega. Determine the velocity and acceleration of the rod as a function of theta. So there is a theta here which measures the angle of the diameter to the horizontal plane, and we want to find the velocity and acceleration of the rod as a function of theta. So solution, we identify the datum. Okay, you can see from the diagram they already have identified this as the datum. So we are solved. Got number 1 already, and then we draw the positive displacement direction. Already the question has shown to you that this is x positive to the right, so this is number 2. Okay, and then number 3 is identify the relevant geometry. So the geometry here, usually there is a triangle that we are looking at, so that's the geometry. Okay, so that's number 3. And number 4 is for I write the equation for the displacement. So when you look, I'm redrawing the triangle there. So this is r, this is r, this is theta, and this is x. So this is also theta lah. So we can find that x is equals to this component and this component. So we can write that x equals to, or let me use a red color here, x, so let's use a red color here. So x equals to 2r cos theta. X equals to 2r cos theta. So that's our equation of motion. Okay, and then differentiate to get the velocity and acceleration. So x dot equals to dx over dt. So d over dt 2r cos theta. So that's equals like r is constant, so we can put 2r d over dt cos theta, and we will have x dot equals to minus 2r sin theta, theta dot minus 2r minus sin theta, and then theta dot. Okay, and you can proceed with the same thing. So we can rewrite it more clearly here. X dot equals to minus 2r sin theta times theta dot. Let's block this equation. So if you want to find the acceleration, let's move to a clear plate. So we have x dot minus 2r sin theta, and then theta dot. Okay, so we want to find the x double dot equals dx dot over dt. So we have to differentiate the whole expression here, minus 2r sin theta, theta dot. So we can do that in turn. So we can take out the constant out. So we can see that this is equals to, so that we can see that this is equals to minus 2r d over dt sin theta, theta dot. So we can say that minus 2r, big expression, theta dot d over dt sine theta plus sine theta d over dt theta dot. So it's against minus 2r big theta dot. Whenever we have sine theta, we will have, so we have cos theta and theta dot plus sine theta theta double dot. Yeah, so the long expression is, and then we know that theta double dot equal to alpha, so minus 2r omega square, so 2r theta dot square cos theta, okay, plus theta double dot sine theta. Yeah, so we can replace this with alpha and this with omega, so it becomes minus 2r omega square cos theta plus alpha sin theta. So that's your answer to what x double dot is. The whole expression is the acceleration of the rod. That's answer. Acceleration. So this is one example for you to look at and try to understand the relationship. I just want to cover these two examples because more than that is, if you look at the books, these are the book will show you the relationship of the expressions, and it's just a geometrical relationship, and we will cover that in the next lecture, where a more complicated structure will be discussed in order for us to apply the technique to a machine, like for example an IC engine. So please review this slowly and identify the differentiation rules that you are going to use in your solving of the equation. Okay, thank you for your attention. We'll see you in the next lecture.